In this video we're going to discuss double integrals over general regions and work an example. So just as to recall what the definition of the double integral is, it is defined via Riemann sums. Alright, the definition at the bottom of the screen here is for the double integral over a rectangle. Again, the idea is cut up the region into many small pieces, pick a point from each piece, plug it into the function, multiply it by the size of that piece, and then add up all of the results. Okay, and that is the definition we see at the bottom. It's a limit. It's a definition defined in terms of a limit, right? Derivatives and definite integrals are limiting processes. A couple remarks about that. The definition is great. Right, theoretically, it's the correct thing, but it's very difficult to compute double integrals using it. We're going to see that we're going to compute those using Fubini's theorem and iterated integrals. All right, but we do need that definition to maintain some basic properties we know about integration, that we can integrate term by term, and that constant factors can be taken outside of integrals or they come along for the ride for double integrals and triple integrals. We'll see. Alright, also we have a geometric interpretation for double integrals. If we have a positive function, the double integral is going to represent the volume under the graph, above the rectangle or the region that you're integrating over. If the graph happens to be above and below, then the double integral is going to represent the net sign volume between the graph and the xy plane. So similar up one dimension from what we had for single variable integrals, that we have the double integral representing a volume. Single variable integrals, remember, could be interpreted as areas under the curve. This is going to be the volume under the graph of the two variable function. Alright, now if we are integrating over a non-rectangular region, we still can interpret that double integral as a volume, and that's what we're going to be addressing in this video. Okay, moving on. We're going to be looking at other types of regions besides rectangles, and in the previous video we explained what Fubini's theorem was over rectangles, and that we could express the double integral as an iterated integral. And we're going to have a similar result for functions defined over regions that are not rectangles, and we're going to classify these as type 1 versus type 2 regions. In a type 1 region, we have a well-defined top and bottom of our given region, and we're going to integrate by letting x vary from, say, a to b, or whatever the left side and the right side of our region are, or the leftmost point or the rightmost point of our region are, and for each x in between those, we're going to let y vary from the bottom to the top of our region. I like to refer to this as vertical slicing with the type 1 region. All right, we're also going to have type 2 regions, and for various problems, one might be better than the other. One description could be better than the other. Some regions could be cast as both type 1 and type 2, but a type 2 region has a well-defined left side and a well-defined right side, and we're going to let y vary from the bottom to the top, and for each one of those individual y values, we're going to let x vary from the left side to the right side. So we're thinking about that as like a horizontal slice. Really what we're doing is parameterizing the region, describing the region, and covering each point inside the region by an x and a y. And now we have Fubini's theorem. This is from the OpenStax book. This is called the strong form of it, and really what we're saying is that we can express this double integral as an iterated integral, and for type 1 regions, it's going to be a dy dx integral. So the inner integral is dy, the outer integral is dx. For a type 2 region, we're going to have a dx dy integral. The inner integral will be with respect to x. The outer integral will be with respect to y. Alright, so the only difference between this and the Fubini's theorem we talked about in the previous video is that we have on here variable limits of integration on the inner integral. Okay, so let's just highlight those. And the inner limit of integration might depend on x if we're doing a dy dx integral, all right, and often will, and it will often depend on y if we're doing a dx dy integral. The inner integral is with respect to x. One thing to note is the outer limits of integrations always have to be numerical. So what I just highlighted in yellow there has to be numerical constants. Alright, we're going to look at an example in this video to finish this up. Alright, here's the example. We've got the double integral of the function y with respect to area over this region R, where R is the region in the first quadrant enclosed between the circle x squared plus y squared equals 25 and the line x plus y equals 5. And I've got the picture below. We're going to do a little bit of the visualization of this in Maple, and then we'll come back here to work this problem out. Alright, so what I've got here graphed in Maple is the same example, and to understand how or what the region we're looking at is, you could plot in Maple or using Desmos the entire graphs. So I've got x squared plus y squared equals 25, which is the circle shown here, and then the line x plus y equals 5. Alright, we've got that plotted also, and we want the region enclosed between the circle and the line in the first quadrant. So we're looking at this region right here. Alright, now that's the region we're focusing on right there. Alright, getting rid of the rest of the graph. So notice we have to find where these two graphs intersect. Alright, and they intersect at 0, 5 and 5, 0. Alright, now there's a couple of ways we can set this problem up. This region happens to be both type 1 and type 2. We're going to set this up by using vertical slicing as a type 1 region. So notice when we go from the left side to the right side that the slice changes in height. Alright, so as we go from the left side to the right side, so for one fixed x value, we're going to be slicing from the bottom to the top of this region, and those y values change as x changes as we're going across. Alright, as we're going from 0 to 5, the bottom and the top changes with x. Those y values change with x, and that's why we are going to get a inner integral which is going to be dependent on x. The limits of integration are going to depend on x. Alright, so going back over to OneNote, let's see how we're going to analyze this. Okay, so let's get to work on this here. Alright, one thing we're going to be doing in a lot of these problems is solving the given equations for either x or for y. Solving the line for y, we get y is equal 5 minus x. Solving the equation x squared plus y squared equals 25 for y, if we subtract over the x squared, we get y squared equals 25 minus x squared, and extracting square roots, we would get plus or minus the square root of 25 minus x squared. Now for us, the upper curve here is the square root graph. That's the circle, and we only need to consider the positive square root here. We're talking about it in the first quadrant. All right, where y is non-negative, y is positive there. All right, the graph, the lower one, is of y equals 5 minus x. So how do we want to set this integral up, this double integral up? Well, what we're going to say is we're going to let x vary from the left side, which is 0, to the rightmost x value, which is 5. For each x in between, I'm going to draw a generic x on here. We're going to let y vary from, so going up your screen, up from that x value, we're going to let x vary from the bottom to the top of that region. All right, I like to draw a vertical slice in there. All right, and then indicate, well, what is the y value at that particular, above that particular x? Well, it's 5 minus x, and it's going to range up to the top, which is 25 minus x squared. All right, so now when we go to set our double integral up, we're going to keep that in mind. So again, our problem is do the double integral over this region R of the function y with respect to area. Fubini's theorem is showing we can do this as an iterated integral, and we're going to rewrite this then as the integral. I'm just going to do this below here. Alright, the dA is going to turn into, what we're going to be doing is letting x vary from 0 to 5. For each one of those x values, we're going to let y vary from the bottom of the region, which is 5 minus x, to the top of the region, which is the square root of 25 minus x squared. All right, and we've got then our function, our integrand is still y here. Now the dA part is going to turn into, in this case, dy and then dx. Okay, we want to think about this as our inner integral and our outer integral there. All right, and I put the emphasis on the limits of integration, that x is ranging from 0 to 5, and for each x, y is ranging from 5x to the square root of 25 minus x squared, just to help emphasize that the inner integral is with respect to y, the outer integral is with respect to x. Okay, now we have to go through and evaluate this integral. All right, and so to do that, we have to use the fundamental theorem of calculus, for the single variable version, but we have to find the anti-partial derivative of this function with respect to y. So what's the antiderivative, or the anti-partial derivative of y with respect to y? Well, that's going to be 1/2 y squared, just like in calculus 1. So we're going to have our outer integral staying the same. Now we've taken care of the inner integral. It's going to be 1/2 y squared, and now we need to evaluate this by plugging in y equals the square root of 25 minus x squared, and plugging in 5 minus x for y and subtracting the result. And then we need to take that result and we're going to have to integrate that with respect to x. So for these problems, typically the toughest part is the first step, getting the first inner integral correct after we get it set up. All right, now we just need to plug in and then simplify. All right, so I'm going to drop the dependence on x on the upper and lower limits of integration. So we're going to have 1/2, and then I'm going to leave the 1/2 outside. We need to plug into y squared, that's our antiderivative, those expressions, and then do the appropriate simplification. So we got to put in the square root of 25 minus x squared, and then also put in 5 minus x here and square those functions. Squaring the square root will make conveniently that square root go away. We can pull the 1/2 outside the integral, and we're left with 25 minus x squared. Now we need to square this binomial out. All right, when we square that binomial, we get 25 minus 10x plus x squared. All right, and then we have to distribute the negative sign through the parentheses there. All right, doing that, I'll just rewrite it and then we'll combine like terms. We get minus 25 plus 10x minus x squared. All right, and we're going to see here is that the 25 terms cancel out, but the other couple terms combine there. So what are we left with? In this case, we're left with 1/2 times the integral from 0 to 5 of, we have negative 2x squared and then plus 10x. All right, so now it boils down to a single variable integral. All right, so we know how to handle these. So just antiderivative, applying the fundamental theorem of calculus again. So antiderivative here, we're going to get minus 2/3 x to the 3rd power, increasing the power by 1, or by 1 to 3, dividing by that new power, and then we would get 1/2 x squared, but the 1/2 times 10 will give us 5x squared. And then we need to plug in 5, plug in 0, and then subtract the results. Okay, so just need to finalize this here. So what do we end up? 1/2 minus 2/3 times, put in 5 to the 3rd power is 125, plus 5 times 5 squared is 25. When we plug in 0, 0 cubed and 0 squared is 0, so it wipes those terms out, so I'm not even going to write that down. All right, and then just to clean this up to finish, we get 1/2 times, we're going to get negative 375 over 3. This is really 125, all right, over 3. Okay, I've got a little mistake here. I got ahead of myself a little bit. Multiplying that by 2, we get minus 250. 125 over 1, put that over 1, multiply the top and bottom by 3 to get a common denominator. We'll get 375 over 3. And then just finally adding the results, we're going to get 125 over 3 times 1/2. And so the final answer for this problem is 125 over 6. All right, so I'll just rewrite that. So our double integral comes out to exactly 125 over 6. And that's it for this video.